So here we go. The valence bond picture said that atoms and molecules were held together by overlap of valence orbitals forming localized electron pair bonds. Those electron pairs, sigma, pi, whatever they are localized between the nuclei, and because of that, they stabilize the two nuclei. The bonded atoms are more stable than the unbonded atoms. Okay. The molecular orbital picture takes an entirely different approach. So think about this for a minute. The molecular orbital picture says, in essence, that a molecule, in some respects, is just like an atom, in that it will have its own set of orbitals. And those orbitals are, they have a shape, they have an energy, they can hold electrons just like atomic orbitals. They are in many respects just like atomic orbitals, but in one important respect, they're different. They are capable of looking at the whole molecule at once. Instead of just being a localized electron pair bond, if you put a pair of electrons in a certain molecule, in a molecular orbital, they may spread out over the whole molecule. Now, what's good about that? If you can spread out electron density, you're always better off, right? Because electrons repel one another. So the idea of delocalization is a very favorable one, and this model leads us right to it. In the molecular orbital theory, a molecule is pictured as a collection of nuclei with electrons in molecular orbitals delocalized over the structure. Like the atomic orbitals, molecular orbitals of molecules have specific energies and shapes. The molecular orbitals are conceptually formed by a combination of the wave function of atomic orbitals. And this is done by what's called a linear combination of atomic orbitals. Well, don't worry about that. Mathematically, since we're only dealing with diatomics, the linear combination is we're either going to add them or we're going to subtract them. So math, it's not going to be big deal math here, right? We're going to just take the simplest possible approach, and that's LCAO, linear combination of atomic orbitals. Now, when you do that, you get a new wave function for each molecular orbital. And that wave function itself, just like the atomic orbital wave functions, produces information about the molecular orbital, like its energy and like its shape. So here is how we go about this. We're going to take a, let's say we take H2. We'll take the atomic orbitals, the two 1s orbitals on the hydrogens, and we're going to do a linear combination of them to make two molecular orbitals. In this case, two atomic orbitals, you get back two molecular orbitals. It's a fair deal. No charge on your credit card. Okay? So atomic wave functions are put together, combined mathematically to produce molecular wave functions. The nice thing about this is for simple molecules like these diatomics, you don't really have to do any mathematics except add and subtract. And you don't really add and subtract any numbers. You add and subtract the atomic orbital shapes. All right. Now, basis for this, since it's a linear combination, is that the number of molecular orbitals formed is always equal to the number of atomic orbitals that combine. Okay? Now, when can you combine atomic orbitals? That question doesn't appear on this slide. But I want you to think about it because there is a pretty simple answer. In order to combine two atomic orbitals to make molecular orbitals, two things have to be true. One thing is the AOs have to have same symmetry. In this case, sigma or pi. They either have to be both sigma or both pi. And we know what sigma and pi means, right? We've gone through this from the valence bond model. So they have to have the same sigma, the same symmetry, either both sigma or both pi. And the second thing they have to have is similar energies. If they have similar energies and the same symmetry, they will combine to form molecular orbitals. If their energy is very different, then probably it's not a molecular compound anyhow. It's an ionic compound. As you would find that in cases where you had a metal and a non-metal, right? Okay. Questions on this little brief introduction? Okay. Now, I put down here at the bottom www.falstat.com/QMMO. If you have an interest in this at some point, and there might be somebody in the room who does, Professor Paul Falstad has a nice website where he shows you Java programs that actually do the combination. They do the math for you and let you see what happens when you bring two atomic orbitals together and combine them, either add them or subtract them. So it's there. So let's suppose we take H2. So we have hydrogen atom A and hydrogen atom B, and we have two 1s atomic orbitals here. And as long as they're separated, they're happy. But if we bring them together to where they start to overlap, this model says you will get two molecular orbitals because you're starting with two atomic orbitals. All right? One of the molecular orbitals you'll get comes from combining the two wave functions with a positive sign. And the other one, the peculiar one, the one that you probably haven't seen before, or maybe don't remember, is the one where you take a negative sign. And a whole new thing happens that valence bond doesn't have anything about. So let's look at it for a minute. The psi 1s wave function for hydrogen atom A is plotted on this diagram. It's a dotted line or dashed line that looks like this. This is the nucleus of hydrogen atom A right here. And here's hydrogen atom B, and here's its 1s wave function. And this is electron density going up in this direction, or amplitude of the electron wave if you prefer. In the middle, between these two, the overlap occurs, and in this region right here, when you sum these two, there will be an increase in the available electron density, and that will stabilize the molecular orbital that you get by adding these two. It's that one right there. Okay? That is called a bonding molecular orbital because the application of the positive sign causes there to be more electron density in the middle here where it does the most good than was the case for the two isolated atoms. And in the end, that makes the bonding molecular orbital lower in energy than either one of the atomic orbitals, which I'll show you in a minute when you get to energy level diagram. Now, if you take the difference between the two, here's the shape of the bonding molecular orbital. And incidentally, it's called sigma for the same reason that we talked about sigma bonds and valence bond. It comes from head-on overlap, right? And it's called sigma 1s because it's the 1s wave functions that we combine to make it. Now, if you take the negative combination here, here's the negative sign, what happens? Well, you change the 1s of hydrogen B, you put a negative sign in front of it, and that makes its amplitude go down like this. And in the area between the nuclei, the positive and the negative overlap to cancel. This is just the same thing that we saw for wave cancellation. We had wave reinforcement, wave cancellation. This is wave cancellation in the middle. So in this molecular orbital, we have what's called antibonding characteristic. That's new, isn't it? Probably you haven't heard that. Antibonding molecular orbitals look much different. They have a node in the middle, a place where electron density can't be. And they look, in this case, something like this. It's like an extremely nearsighted person here. the node in the middle comes from the area here where the waves cancel. The nuclei are still there, and what doesn't cancel is on the outside of them, so it doesn't contribute anything to the bonding. So if you put any electrons in here, what really happens, and you have this functioning molecular orbital, is these two positively charged nuclei are looking directly at one another. And coulombically, it's a very repulsive interaction. So the node causes this thing to be unstable or higher energy. So the bonding molecular orbital goes down in energy, the antibonding goes up. So if we want to talk about the energy level diagram and the shapes, we've seen the shapes. We start in the case of the energy diagram with two isolated hydrogen atoms, 1s, and if we combine them, we get if we add them, we get a bonding molecular orbital, which is lower in energy. Shall I wait until you folks are done? Okay. We get a bonding molecular orbital that you recognize here that's lower in energy. And if you take the difference, charge delocalization is what makes this, one of the things that makes this more stable when we put electrons in. We take the difference, then we get the antibonding one with the node in the middle here. And therefore, this thing is at higher energies. So we took two atoms, we took their valence orbitals, and look what happened. We haven't said electron once. You see any electrons? You don't even talk about electrons until you've done the molecular orbital construction and have the energy level diagram. So at this point, the description, the molecular orbital description of H2 is it has sigma 1s, low energy bonding molecular orbital, and sigma 1s, this is called sigma 1s star. You see the star right there? That means it's an antibonding orbital. Antibonding. Now, if you put electrons in the bonding molecular orbital, it makes the molecule more stable. And we'll see in a little bit, those electrons contribute to making the bond order larger. There's a bond order definition for molecular orbital too, or also. Okay. The antibonding molecular orbital, having a node between the nuclei, causes nuclear repulsion, and it makes a sigma 1s less stable. So bonding molecular orbital, more stable, lower energy. Antibonding, unstable by comparison, less stable at least. Okay, now that we have the molecular orbitals, I'm ready to put them into the diagram. The electrons. And the rules for this game are entirely already known to you. They use the Aufbau principle, the Pauli exclusion principle, Hund's rules, all the things you already know about. They apply to the molecular orbital diagram equally well. Nothing new to learn there. Isn't that good? So the order of H2MO energies is the energy of the sigma 1s is lower, meaning more negative, than the energy of the sigma star 1s. Now each molecular orbital has a capacity of 2 electrons. In other words, it can have 0 electrons, 1 electron, or 2 electrons. If it's 2 electrons, the Pauli exclusion principle says, whoa, the molecule can't exist, won't be stable unless those two have opposite spins. But that's all known to us. So orbitals of equal energy, like 2 orbitals of the same energy or 3 orbitals of the same energy, will be half filled because with the spins parallel because of Hund's rules. So that's all known to us. Here's something new. The bond order for that molecule is determined after we put the electrons in, and it is equal to this equation, 1/2 of the number of electrons in bonding molecular orbitals minus the number of electrons in antibonding molecular orbitals. As we'll see in a little bit, all that is a focus, all it needs to be is a focus on the valence molecular orbitals. The core molecular orbitals don't play a role in this. All right, so now I offer you this diagram. This is the molecular orbital energy level diagram that applies for any two atoms that use two s orbitals to form their molecular orbitals. This would work fine for H2 or He2 or Li2, anything that forms a bond by combining two s orbitals. Now, our process is going to work like this. You put the atoms, the combining atoms, on the left and on the right. Energy is increasing in a vertical direction. You put the molecular orbitals in the middle. So this is the molecule, H2, and this is the H2 orbitals here. And you could see their picture. Here's the bonding molecular orbital, sigma 1s. Here's the anti-bonding one, sigma star 1s, right there. So what do? We count the total number of valence electrons in the atoms. Okay? Each hydrogen comes with one electron, so we'll put one electron there and one electron there. Now we just count them. There are two. Those two electrons are used to fill up the molecular orbitals according to all the rules that we just talked about. Nothing new, nothing hard, simple as it could get. So we have two electrons, and we have a sigma 1s at lower energy. We're going to put those two electrons right there. Are we going to put any electrons up in the antibonding? No, we've already used them. There aren't any more. You would have to have more electrons available at this point to put them up there. This one's filled. So the molecular orbital electron configuration for H2 can be directly written down. It's sigma 1s with two electrons. Okay? So that's how you describe the electron configuration of a molecule. Sigma 1s with two electrons. Now the bond order will be 1/2 of the number of electrons in bonding molecular orbitals, which is 2, minus, quantity in parentheses, that is, the number in antibonding, which is 0. So 1/2 of the quantity, electrons in BMO minus electrons in ABMO, antibonding molecular orbital. Okay, that's 1/2 of 2 minus 0, and that tells us that the bond order, according to this molecule, to this model, I mean to say, for the H2 molecule, is 1. So that's like saying in the valence bond model, there is a single bond there. Okay, so there is a parallel between what this equation gives us in the molecular orbital model and what our usual picture for bonding in the valence bond model, which is now right in the back of your head and you're not thinking about it. Right? All right. Now, what I'm going to show you is that this equation is more general than the method that we use for getting the bond order for the valence bond described molecule. But they both go towards the same result. That is to say, a bond with a molecule with a bond order of 1 should be a stable molecule. It has a bond. Right? So we could say, general rule, take note of this, a bond order greater than 0, all that has to be is greater than 0, indicates that the molecule or ion is more stable than its parent atoms. In other words, forming the molecule is downhill energy-wise from the atoms. So it doesn't have to be 1. It can be less than 1. But it can't be 0. It has to be more than 0. And in general, the higher the bond order, the stronger the bond. So this, I hope you find this comfortable. There's very little that's new here except the antibonding orbital. And that antibonding orbital gives us something that the valence bond model doesn't give. You may wonder, why don't we just all use the valence bond model? We could do that. Well, the problem is that even though it does a good job on lots of organic molecules and so forth, it fails. And it fails in critical places. And the one that's always cited at this point is it fails to adequately describe the dioxygen molecule. I'll show you this in detail later. but the valence bond model doesn't get it right. And so you know what happens. You can't get through my course without knowing what happens when a model fails. You either modify it or you can it. And the valence bond model has not been modifiable to take care of these things. The molecular orbital model, on the other hand, gets it right. And I'll show you that later. Okay, so let's apply it to something. Back in 1868, there was a very widespread solar eclipse. And many physicists used the solar eclipse as a way to look at the light coming out of the sun when the moon blocked the bright light that flooded everything. And a French physicist found some lines in that light that he thought corresponded to something new. There was another scientist at the time that also saw these lines. The prediction that he made was that this is a new element that exists in the solar atmosphere. And so he called it helium, after Helios. And so helium was discovered in the atmosphere of the sun before it was discovered on Earth. And among other things, when it was discovered on Earth, it was discovered that a state in the U.S. by the name of Texas has more than almost anybody. Because it's a component of natural gas. And out in West Texas, there are natural gas wells that have significant amounts of helium in them. Only for them can we have superconducting anything. And we're using helium at a phenomenal rate. When it runs out, there's nothing to replace it. So don't buy helium balloon. Okay? Remember, Geanangel told you, in your lifetime that helium's going to run out. How they're going to do MRIs and things once that happens is problematic. Okay. Is there such a thing as He2? Now that we know there's helium, is there a diatomic helium? Well, it turns out that one of the early successes of the molecular orbital model was to predict the existence of a molecular ion which was formed when you passed electric discharges through helium gas. He2 with a positive sign. 2 helium nuclei and 3 electrons. Okay? If you think about this, helium uses the 1s atomic orbitals just like hydrogen. So you would use the same molecular orbital diagram. You don't have to have a new one. It has a sigma 1s and a sigma 1s star. And the only thing that's really different, besides the more protons in the nucleus, is that we have 2 electrons for an He and 1 electron for an He+. So we put them over here. This is He+, 1 electron, and this is He with 2 electrons. Then we add them up. Count the electrons. There's 3 of them. And when we do that, we put the first 2 in the sigma 1s and 1 in the sigma 1s star. And we calculate the bond order. Well, the bond order is based on the electronic configuration, molecular orbital electron configuration. Sigma 1s with 2 electrons, sigma star 1s with 1. Count them up. 1/2 of 2 minus 1 is 1/2. And you might say, 1/2, what's that? That can't be worth much. I wouldn't want to be hanging from a ledge with a bond order of 1/2 holding me there. But the rule is that the thing is more stable than its component or its parent atoms if the bond order is anything over 0. This is, and this predicts that He2+ should be a stable species. And it's seen in the gas phase, and in fact, it's seen in the surface, the atmosphere of the sun occasionally, I understand, too. Now, what about He2? Well, you right away see there's a problem. For He2, we have 4 electrons. Okay? And so if you take those 4, that makes sigma 1s2, sigma star 1s2. Sigma 1s2, sigma star 1s2. Bond order 1/2 of 2 minus 2 is 0. So this model predicts that 2 helium atoms can't form a diatomic molecule. And in fact, it's only He2 is almost completely unstable. The only time you see it is when you remove almost all the energy from helium gas, and you get a very, very weak combination of 2 helium atoms. As soon as you let in the tiniest bit of energy, they fly apart. So this is an unstable species. You can't get it in a jar, and it's not ever going to be an important molecular species as far as this model says. Okay, let's apply it to the model, that is, to 2 other cases. In this case, 2 ions, H2 plus, H2 minus. H2 plus was seen all the way back when J.J. Thomson was passing an electric discharge through gases when he was studying cathode ray tubes. It had been seen for a long time, and it was seen also in the very first mass spectrometer. So that one exists. H2 minus would have 1 more electron than H2. H2 plus would have 1 less. So if we look at this, both of them, of course, use the same molecular orbital diagram. We get a lot of use out of this diagram because they both start with the 1s orbitals. And our process goes then as follows. We count the electrons. We have hydrogen here. It has 1 electron. Put it in right there. Then we have H plus over here. Its electron's gone. It's just a proton. So no electrons go in there. So adding it up, there's only 1. The 1 goes in here. The molecular orbital electron configuration is sigma 1s with 1. And with 1 electron, the bond order is a half. And like He2 plus, H2 plus should be stable. Questions on that? It's really very simple. The diagram's simple and the counting is simple. If that predicts that H2 plus ought to exist, and in fact it does. If we look at H2 minus, that's 3 electrons. And we use the same diagram. We have hydrogen 1s and hydrogen H minus here, 1s. In order to get to H2 minus, we need an H, and we need an H minus. And then the molecular orbitals for H2 minus would be a sigma 1s and a sigma 1s star. They look familiar, I bet. So we count the electrons. There should be 1 electron right there. And then here there should be 2 electrons, right? H minus would be the electron that came with the hydrogen plus 1 more for the sign. Okay? So we put them in. Look what happens. Sigma 1s with 2 electrons. Sigma 1s star with 1 electron. Does that look familiar? Well, it's very much like He2 plus, right? Here's the electron configuration. And the bond order is 1/2 of 2 minus 1 is 1/2, and therefore we predict that H2 minus can also exist. It does exist, but it's very unstable. But it can be seen under the right circumstances. Okay, questions on H2 plus or H2 minus? All right, now let's take 1 step down in the periodic table, go to the second period, and talk about the elements in the second period, starting with lithium. The homonuclear diatomic molecules, lithium 2 through neon 2. That's going to be our focus for the rest of this course. The S-block diatomics, Li2 and Be2, use the 2s atomic orbitals. Not the 1s, but the principle is exactly the same. Okay? First of all, here's lithium. Its valence, its electron configuration is 1s2, 2s1, and it has 1 valence electron. The 2s is higher in energy than the 1s, and therefore the sigma 2s and the sigma 2s star ought to be higher in energy than the sigma 1s and the sigma 1s star. Okay? So here's what the diagram looks like. Now, I want to point out to you, here is one of the lithiums on the left, and here's the other one on the right, and here's the dilithium molecule. Now, if there are any Trekkies left around. This dilithium is not the same as that which powers the Star Trek Enterprise. That's a solid, and I understand its characteristics are different. This is a molecule. Okay, so I can't get in trouble with dilithium here. So here's what we're going to do. We've got the molecular orbitals, sigma 1s, sigma 1s star, sigma 2s, and sigma star 2s. And I'm right away going to point out to you that the 1s orbitals are core in lithium, and the 2s is valence. So we can draw a line right across above the sigma 1s, and everything below that is core. And there's no bonding that comes from the interaction of core orbitals. They're too stable. Above that is the valence. That's where the bonding comes from. So if we want the electron configuration, we use the valence and the core together. If we want the bond order, we just use the valence. So count the electrons. Each lithium comes with 3. Li2 would have 6. 2 of them would be valence. So we're going to fill up things here. Let me turn my pen on. First of all, for the lithium on the left, 1s, 2, 2s, 1. You can do this. It's not hard. Lithium on the right, 1s2, 2s1. 6 electrons, 2 are in the valence, and 4 are in the core. 6 electrons, 2, 4. Those are the 4 core electrons. And now there's 2 left, and they go in the sigma 2s, and they're in the valence. Now let's think about this a minute. The electron configuration includes both the core and the valence, just like it does in an atom, right? We said lithium's electron configuration is 1s2, 2s1. We include both the core and the valence. We do the same thing for Li2. So if you get a question about what is the electron configuration for a diatomic molecule, include both the core and the valence. Okay? Now, to calculate, the next thing to do would be to calculate the bonding molecular orbital. The bond order from the molecular orbital. So all we have to do in that case is look at what's above the line. We don't have to worry about the core. So we have sigma 2s with 2 electrons, sigma star 2s with none. So the bond order is 1/2 of 2 minus 0, and that's 1. Okay, so that suggests that the dilithium molecule has what you might call just a single bond. And its bond energy and its properties are in complete agreement with that. So the model predicts Li2 molecule to be stable. Now, it is stable, but only in the gas phase. In the solid, what happens? What's lithium in the solid?
Crystal.
Well, it's crystalline, or it's a metal. It's metallic. Okay, so there's something about the metallic state that gives lithium some extra stability compared to the Li2 molecule in the gas phase. But it's okay. You can get this Li2 in gas phase. Okay, let's go one more step to the right and look at beryllium. Beryllium has an atomic electron configuration of 1s2, 2s2. Its Z is equal to 4. Question?
So the numbers were different from our handout in the last slide.
What did I say wrong?
It's just because you said just use the valence electron, so the bonding order was 4 minus 2 instead of 2.
If you included all of the electrons, you get the same answer. I see what you're getting at. Let's just do it. Since you suggested it, let's have a look at it. Let's just try to calculate the bond order with all the electrons and see what happens. All right, so remember, 3 and 3. And now we have 6, so let's put them in. 2, 4, 6. So now the bond order would be equal to 1/2 of, now how many electrons are there in bonding molecular orbitals?
4.
There are 4, aren't there? How many are there in antibonding molecular orbitals? 2. So it's 1/2 of 4 minus 2. Would you look at that? It's 1. So you get the same result. But it sort of implies that these electrons have something to do with bonding, and they don't. A filled bonding molecular orbital and a filled antibonding molecular orbital cancel one another out as far as bonding goes. So I appreciate you pointing that out. I should have fixed that, and I just didn't notice it. You're welcome. All right, what's left? We want to go ahead and do beryllium. Each beryllium atom has 2 core electrons and 2 valence electrons. And that would give, for Be2, a total of 8 electrons. And you already see what's going to happen, don't you? It has filled sigma 1s and sigma 1s star, but now it has filled sigma 2s and sigma 2s star. The valence part of it shows filled bonding and antibonding orbitals. The electron configuration includes it all: sigma 1s, 2 electrons, sigma 1s star, 2 electrons, sigma 2s, 2 electrons, sigma star 2s, 2 electrons. But the bond order is 1/2 of 2 minus 2, it is 0, and the Be2 molecule is thus predicted to be unstable, and except at extremely low temperatures under very strange conditions, no one's ever found a Be2 molecule. Okay. Now, before, we have looked at the combination of 1s and 1s and the combination of 2s and 2s. May I have your attention? Thank you. What's left to do? Well, we were going across the periodic table from lithium through beryllium to boron, carbon to nitrogen, so forth. The next element after beryllium, of course, is boron. Boron has an electron in p orbitals. Okay? And so we need to think about how p orbitals will combine to make molecular orbitals. And the story is pretty simple. If our arrangement has the bond along the x-axis, then the p orbitals between the 2 atoms that are involved, let's suppose it's boron here, or any element that has its valence p orbitals filled, then you would expect to get the combination of 2 p orbitals to give 2 molecular orbitals. And those 2 molecular orbitals would be a sigma 2p, in this case x, and a sigma star 2p x. You can write a little x right there and a little x right there if you like to designate this. What will this look like? Here's the picture. This will be end-on overlap because both of these p orbitals lie along the same axis. So they're going to approach one another as the atoms come together to form the molecule directly head-on. And so the molecular orbital picture takes an LCAO of these, and the first one is the sum of the 2 wave functions. The sum of the 2 wave functions has a big overlap in here between the nuclei, and you can see the picture of it right there. Sigma 2p molecular orbital is bonding because if you put electrons in it, they're localized in the area which will make the bond strong. Okay? So if you add these 2 wave functions, px plus px, you get the sigma 2p bonding molecular orbital. And if you subtract them, of course, you create a node in the middle. And this node means there's no electron density in here, or very little electron density. The nuclei see one another with no shielding. That's a bad thing. Any electrons that are in here are localized, as we said before. So this is going to be an antibonding molecular orbital. Does it make sense to you? Okay? So this works pretty much like an S plus an S molecular orbital. Now what's left? Well, we've used up the px here, So we have the py and the pz, which are both perpendicular to the bond axis. So the bond axis forms sigma molecular orbitals. The p orbitals that are perpendicular to it will form pi molecular orbitals, just the way they did in the valence bond picture. Exactly the same. So side to side, py overlap, for example, gives two pi molecular orbitals, pi 2py and pi star 2py. The picture looks like this. These things are side to side. As the atoms come together, they overlap side to side, this. And if you sum those up, if you add them together, then you get a pi 2py molecular orbital, which is bonding, because it puts electron density in here in the middle of this, between the two nuclei, and that will stabilize the molecule by adding bond energy to it. If you take the antibonding one, you create a node in the middle. You create something that looks like sort of butterfly wings here, where the electron density, if there's any electrons in this antibonding pi star orbital, goes out here where it does no good for bonding the molecule, and the nuclei are again staring at one another, and Coulomb's law will have them, because they have both positive charges, this will be a repulsive state. Okay, so this is the antibonding molecular orbital of pi symmetry. And there will be another one. This was built from the two py's. There will be another one with pz here. And I'm sorry, I apologize. My y's and z's are not right on this diagram. Imagine that this is py up here to match up with this, and this is pz down here. Then the picture will look better. So then there is this second set of pi molecular orbitals that have exactly the same energy as the py's, and they'll come from the pz's. So there will be two same energy pi 2p bonding molecular orbitals and two same energy as each other pi star 2p bonding molecular orbitals. So we combined two sets of three atomic orbitals. So how many molecular orbitals do we get? The first thing we said was the number of molecular orbitals equals what? The number of atomic orbitals, he says, and he's right. So there's 3 p orbitals on each atom here. So 2 times 3 is 6, and we should get 6 molecular orbitals. So here is 1, here is 2. Then there are 2 like this, 2 here, and there are 2 like this. So, sorry, there's one of these, and there's one of these. I'm sorry, I've shifted horses in midstream here. There are 2 of these and 2 of these. So that's 6 altogether. 1, 2, 3, 4, 5, 6. Okay, so we have the molecular orbitals. All we have to do now is put them together and make an energy level diagram. Now, in this case, we note that 2p atomic orbitals are always higher in energy than 2s atomic orbitals, except in one case, hydrogen. Hydrogen atom, they're the same. But otherwise, 2s is always lower than 2p. We saw that back in chapter 8. So that would mean that the sigma 2p arrangement here would be the most stable, the pi 2p next, the pi star 2p after that, higher, and the sigma star 2p would be the highest, and this would all be above the atomic orbital, the molecular orbitals made from the 2s atomic orbitals. So down here somewhere, if we look down here, we would have the 2s. So this is sigma 2s star and sigma 2s bonding molecular orbital. Those are down here because the 2s is over here somewhere, 2s atomic orbital. And above this, then there's the sigma 2p, the 2 pi 2p's, the y and the z. This is x here, and this is y and z. And then the antibonding y and z, and the antibonding 2p sigma star 2px. Now, how do I know that sigma star is above pi star? Well, it isn't always, but it usually is. And normally, the splitting from here down to the corresponding bonding molecular orbital depends on the overlap. And head-on overlap is usually more effective than side-to-side overlap. Does that make sense? Okay, so we have a diagram that looks like this, and here are atomic orbital 2p's here and here, and so then we would have sigma 2p below pi 2p most of the time. Well, if it was just overlap and that's all that did it, it would always be that way. But unfortunately, there are some other things that can affect this, and they are outside the scope of our discussion at this point. But what we can say is, in some cases, pi 2p can be below sigma 2p, reverse of what you see here. So we have to figure out when that is, and all I can suggest to you at this point is I can't give you the tools to figure it out because you don't know molecular symmetry, but if you want to take my senior course, I'll see that that condition gets remedied. So for the time being, all I'm going to tell you is that sigma 2p is usually below pi 2p, but there are some cases where the atomic orbitals mix. And the easiest way to do this is just to memorize where it doesn't mix and where it mixes, or memorize one and assume the other. So what I'm saying here is sigma 2p is below pi 2p as the overlap looks like it should be for dioxygen, difluorine, and dineon. So here's sigma 2p below pi 2p for those. And for the others, B2, C2, and N2, it turns out that pi 2p is below sigma 2p. Does it make a difference? Unfortunately, it does. You cannot ignore it. So what I would suggest is you memorize it. I don't ask you to memorize any more than I have to, but I think this is a place where if you want to get the results right, you need to remember which way the orbital energy order comes out here. Okay. So now if we wanted to figure out what the bond order for these 6 diatomic molecules would be, then we do just pretty much like the Aufbau principle. We start off with a number of electrons. We use either this diagram or this diagram to put those electrons in, and then we use the bond order equation for that. Okay? So we look at this. Here are the 6 diatomic molecules that we're going to start with here. B2, C2, N2, O2, F2, and E2. And notice for B2, C2, N2, pi 2p is below sigma 2p, as I just said, and I hope you're going to learn. And for O2, F2, and Ne2, sigma is below pi. So these are our diagrams. This is one set of 3. This is another set of 3. And we have the following numbers of electrons to put in. First of all, B2, each boron comes with 3 electrons, so B2 would be 6 electrons, right? C2 would be 8, N2 would be 10, and so forth across. So I'm going to show you a picture for each one of these. And the first one is B2. 6 electrons that we fill up the sigma 2s, the sigma star 2s, and the pi 2p, which is lower for B2. Now, this tells us a couple of things. First of all, the bond order for this arrangement is 1/2 of 2 plus 2 is 4, minus 2. 4 minus 2 is 2. 1/2 of that is 1. So the bond order is 1 for the B2 molecule. Now I draw your attention to the yellow graph here, the yellow, the word doesn't come. This is just one way of plotting the bond energy, and the height of this is proportional to the bond energy. It happens to be 219 kilojoules per mole for the B2 molecule. So that's one thing. It's based on this electron configuration down here that, of course, is based on the diagram. You write the configuration from the diagram. Now, the second thing is that the B2 molecule is very unusual. It's one of only a small number of diatomics that's paramagnetic. What's paramagnetic mean? Anybody? Has what? It has unpaired electrons. In this case, it has 2 unpaired electrons. And it's Hund's rule that causes this to happen. This electron 5 and 6 have to end up with parallel spins, the same energy. Okay, so B2 is a rather unusual thing, but it is stable in the gas phase. All right, now let's go to the next one here, which is C2, and we have 2 more electrons. We're stepping one more step to the right in the periodic table. Carbon has 1 more electron than boron does, so 2 carbons have 2 more electrons than B2. Okay, so where do we put the electrons? You're right, we fill up the pi 2p. What would be the bond order now? It's 2 plus 4 is 6, minus 2, these are antibonding one here, is 4, divided by 2 is 2. And is this molecule diamagnetic or paramagnetic? It's diamagnetic because there are no unpaired electrons. You're right. Okay, so those are the things we can tell from this. It has the equivalent of a double bond. Look at this yellow bar here, 620, a little over twice as much as the bond in B2. So that fits pretty well with the bond order. And the molecular orbital model gets it right. Okay, questions on C2? C2 again is a gas phase thing. We don't get that in the bottle. If we go one more step, 6, 8, 10 electrons now. So we fill this up, sigma 2s2, sigma star 2s2, pi 2p4, sigma 2p2. What would be the bond order of this guy? Well, it's 2 plus 4 is 6, plus 2 is 8, minus 2 is 6, divided by 2 is 3. So this guy has a bond order of 3. It is diamagnetic. There aren't any unpaired electrons for N2. Well, we knew that. N2 is, of course, quite common. One of the famous 7 diatomics. You got it. Look at its bond energy. 945 kilojoules per mole. Again, it fits pretty well with a what you would predict for the molecular orbital bond order. Okay, so we've got B2, C2, and N2. Are you comfortable with those? Does anybody have a question about them? All right, now we're going to go across the line. Once we get across the line to O2, we remember that sigma 2p is going to be below pi 2p. Between N2 and O2 is when it happens. And O2 has these things, sigma 2p below and pi 2p above. That's O2, and N2 has them the other way. So we're going to take one more step. Now we have 2 more electrons. Now in this case, those 2 electrons go into the pi antibonding molecular orbital set here, pi star 2p. You put 2 electrons in pi star 2p, and you're going to have 2 unpaired electrons. All right? Everybody see that? Also, you put those 2 electrons in an antibonding orbital. So if you now calculate the bond order, go ahead and calculate it. Everybody take your pencil and calculate the bond order. You know it's 2 here, but show that it's 2. Okay? Do a quick calculation and confirm the bond order has to be 2 for sigma 2s2, sigma star 2s2, sigma 2p, pi 2p, pi star 2p2. Can you do it? Sure. It's not hard. If you look at it, putting 2 electrons at antibonding molecular orbital takes the 3 that we had over here and reduces it to a 2. And you should be able to see that just based on your numbers that you've done. So this says that dioxygen ought to have a bond order of 2. And look what happens to the bond energy. It drops down from over 900 down to 500. Even though you've added electrons, the valence bond model will say, oh my, how can that happen? You added electrons and the bond got weaker? How's that going to happen? That's why we don't use the valence bond model. It gets it wrong. It absolutely gets it wrong. So, 2 things about dioxygen. It has a bond order consistent with a double bond, and it has 2 unpaired electrons. We're going to come back to that. I'm going to show you the experimental evidence for part of that. Let's go ahead, though, to F2. F2 has yet 2 more electrons, and they fill up the 2 remaining spots in the pi star 2p. That leaves you with a bond order of 1, and it leaves you with no unpaired electrons. So F2 is a diamagnetic diatomic molecule. Okay? So as you go across here, what's happening to the bond strength of these diatomic molecules? Well, oxygen has a pretty strong bond. Fluorine, on the other hand, is about 160. It has a very weak bond, even for a single bond. So it's a highly reactive molecule. F2 is not something you want to mess with. It is exceedingly explosive. It gives off lots of heat, and it's a dangerous molecule to work with. Okay, we got one more step, and I think you could see what's going to happen when we add 2 more electrons. They're going to go up here in the sigma star 2p. So when that happens, now all of the molecular orbitals are filled. That guarantees that the bond order is going to be what? 0. So any 2 doesn't exist. The only time you see anything that's like a diatomic Ne2 molecule is exceedingly low temperatures, very low, absolute 0, where the thing cling together weakly. As soon as you warm it up, those neon atoms go their separate ways. There's no bonding. There's no chemical bonding there. Okay, so the molecular orbital picture. I hope you appreciate this because if you try to do the same thing we've done with the valence bond picture here, you really run into quicksand in a hurry. The molecular orbital picture gets it right again and again and again. And so that's why we take the time to include it in this course, because every student of science ought to know about it.
This magnet is very strong.
Hold on a minute. Let me see if I can turn this up. I'm going to show you a little video clip that proves that dioxygen is paramagnetic.
This magnet is very strong. The poles of the magnet are 1 centimeter apart. Focus your attention on the poles of the magnet. The Dewar flask, or thermos, contains liquid nitrogen at a temperature of 77 kelvins.
It just pours straight through. Liquid nitrogen. The magnet's cold.
The test tube contains liquid oxygen at a temperature of 90 kelvins.
See the difference? The liquid oxygen is held in the magnetic field until it all evaporates.
The residual white solid is ice, which formed from water in the atmosphere.
So that proves that dioxygen is attracted to a magnetic field, something we said paramagnetic substances were, whereas dinitrogen is not. Okay. So if we look at dioxygen, and I have resisted looking at it until now because I didn't have a good explanation for its properties. It is paramagnetic by experiment. But in the valence bond model, if you try to apply the valence bond model to understand why it's paramagnetic, you can easily draw a Lewis dot structure which is non-octet and has 2 unpaired electrons. But if you take that one, even as one resonance form, you predict a single bond. So you can account for the paramagnetism of O2 by doing this, even though it's a real chancy Lewis dot structure. But if you do it, you come up with the wrong bond energy. If you make it a double bond and you get the right bond energy, then you guessed it, it's not paramagnetic anymore. And if you did resonance forms for these two, that would not be a normal way to do resonance forms because this has a different number of unpaired electrons. And normally you wouldn't do that. But even if you did, you'd get a 1.5 bond and sort of a average of 2 unpaired electrons and 0 unpaired electrons. So it would come out 1, and that doesn't fit the data. So the valence bond picture simply fails on this exceedingly important molecule. So we have to ignore it. We have to use it where it works, but we have to ignore it. The bond energy is 498 kilojoules. It's got to be a double bond. That's too strong for a single bond. And only the molecular orbital model accounts for the bond order being 2, a double bond, and at the same time there being 2 unpaired electrons. Does that make sense to you? I hope it convinces you why we have to use the molecular orbital model for these things. All right. Now here's what I have left for you today. We need to be able to apply this molecular orbital theory to diatomic molecules and the ions that are derived from them. Again, the molecular orbital model works. If we consider, for example, N2 and N2+, both of those are known stable substances, a diatomic molecule and a diatomic molecular ion. If you apply the molecular orbital model to these, it says N2 has, as we saw before, a bond order of 3, which is in agreement with the fact that it has bond energy over 900 kilojoules per mole. Okay, does that make sense? Well, that's what we saw, and that's how the diagram comes out. Now, if you're going to make N2+, you've got to take away 1 electron. If you take away 1 electron, what kind of orbital did it come from? We're going to back up and look. Okay, here's N2. And the highest occupied molecular orbital is where the electron would come from because that's the easiest one to take. You always take the easiest one. And you see, what is this? This is a sigma 2p bonding molecular orbit. So if you take that electron away, that's going to weaken the bond. And if you calculate the bond order, instead of being 3, it's going to be less than 3. Right? It's going to be less. Sorry, I don't have a way to jump directly to this. But the bond order for N2 is going to be 3, and when we go to N2+, it drops down to 2.5, and the bond energy is 841 kilojoules. So in going from N2 to N2+, the bond gets weaker. Well, it's sort of what you'd expect using the valence bond model, right? It gets weaker. There aren't as many bonding electrons. Well, that's an oversimplification because let's look at O2 and O2+. Right? O2, we saw before, has 498 kilojoules per mole, and we said that's very much like a double bond. But what about O2+? O2 plus bond energy goes up from 500 to over 600. How can that be? How can the valence bond model account for something like that? We take electrons out and the molecule gets weaker? Wait a minute, something stinks. That can't be true, not in the valence bond model. Well, if we go back, and we look at O2, the highest occupied molecular orbital is an antibonding pi. So if we take an electron out of it, what's going to happen to the bond order? It's going to go up, right? Because in doing the count, you will have one less electron in an antibonding orbital, so the bond order is going to go up by a half. So here's what we have. Why does the bond energy decrease from N2 to N2 plus, but increase from O2 to O2 plus? Here is the picture that I told you about for N2 plus. The electron came out of a bonding molecular orbital, and for O2 plus, the electron came out of an antibonding molecular orbital. You take this diagram and sit down and calculate the bond order. N2 is 3, N2 plus is 2.5, so it should go down. But O2 goes from 2 up to 2.5, so it should go up. The valence bond model has not a prayer for accounting to this, and even the simple molecular orbital picture gets it right on the money. That kind of thing in science makes lots of people believers, and that's what's happened to the molecular orbital picture. It has been successful. It continues to be successful, and it is a fact of life in science. It's working its way into biology, and it will, as more computing power becomes routinely available, because it's needed for more complicated molecules, eventually I predict it'll be accounting for the properties of proteins and nucleic acids and all kinds of things. It's not quite there yet, but it's getting there.